Okay, hello everybody, and welcome to the INQA seminar for today, Tuesday, the 8th of April. And it gives me great pleasure to introduce today Giulia Salatino from the Scuola Superiore Meridionale in Naples. And Giulia will be talking to us about her research on noise effects on diabatic quantum annealing protocol. Giulia, over to you.
Okay, hello to everyone. My name is Giulia Salatino. I'm a PhD student from Scuola Superiore Meridionale in Napoli. Today I will talk about a recent preprint that we have sent, let's say, which is titled Noise Effects on Diabatic Quantum Annealing Protocols. The work has been carried out in collaboration with Gianluca Passarelli and Procolo Lucignano from Federico II in Napoli, and with Maximilian Maxler from University of Innsbruck, with whom we had the chance to collaborate thanks to the Aurora European University Alliance, and also with Annarita Scocco from Scuola Superiore Meridionale. In this talk, I will first of all briefly mention the basics of quantum annealing in order to introduce the basic concepts of non-stochastic quantum annealing and quench-sweep protocol that have been proposed and that I want to compare in order to solve the maximum weighted independent set problem that I will briefly describe. I will compare the results of the two diabatic protocols, and then I will pass to introducing noise effects in order to probe the robustness of these two diabatic annealing protocols. After having mentioned some tricks that I exploit for the numerical simulations, I will present the final results. First of all, let's talk about quantum annealing. Quantum annealing is a quantum algorithm that deals with the solution of NP optimization problems. What we usually do is considering a time-dependent Hamiltonian that consists in two terms. The first term that is made up of an annealing schedule that in our case decreases linearly in time, that multiplies an Hamiltonian which is set at t equal to 0 equal to hx, which is usually set as a transverse field Hamiltonian whose ground state is easy to be retrieved. This instantaneous Hamiltonian is made up also of a further term that it is made up by an annealing schedule that in our case increases linearly in time, b of t, that multiplies the hz Hamiltonian, which encodes the problem, the optimization problem we want to solve. So the ground state of this Hamiltonian will encode the solution of the optimization problem we want to solve. In terms of energy landscape, what we do is aim at following in time a state starting from the ground state of the hx and aiming at retrieving the final ground state, which is the ground state of hz, that encodes the solution of our optimization problem. If we define delta as the minimum gap that occurs between the two lowest lying instantaneous energy levels of this instantaneous Hamiltonian, we know that if the evolution is low enough, so if the total evolution of the protocol, capital T, is high enough if compared to 1 over delta squared, we know that the adiabatic theorem will hold, and so Landau's inner transitions will be avoided during the protocol. Of course, this is not always the case, and what we might encounter is an energy landscape that in times behaves like this. So what we have is that a gap that closes exponentially with the system size can be encountered, and in this situation, satisfying the condition of the adiabatic theorem becomes extremely difficult. So what is more likely to happen is that the time-evolved state will go over a Landau's inner transition and jump from the instantaneous ground state to the first excited instantaneous state. And so eventually we will not be able to retrieve the solution of our optimization problem. Due to these problems, proposals have been carried out in the past years in order to exploit the diabatic transitions that are characteristic of these energy landscapes. And what we will look at, for example, is proposals that has been recently carried out, and we will refer to these two recent papers by Feinstein et al. Of 2024 and 2025, where they have proposed a protocol that is a diabatic annealing protocol that we will refer to as non-stochastic quantum annealing. In this case, what the authors have proposed to do is to add an additional term in the instantaneous Hamiltonian that acts as a catalyst and that is non-stochastic, that induces a further closing of the gap together with the natural closing of the gap that we encounter without the catalyst protocol. So what we do is encounter a first closing of the gap, in correspondence of which there is a high probability for the time-evolved state to jump from the instantaneous ground state to the first excited state, and a second gap that closes exponentially with the system size that allows us to eventually have a further Gaussian transition that allow us to eventually go back to the ground state that we want to retrieve. So this is what happens to the time-evolved state during the annealing protocol with the non-stochastic term. In another proposal that has been done also in the recent years, and it has been proposed by Looking at Ali in this paper of 2024, is the sweep-quench-sweep protocol. In this case, what we do is not adding an extra term in the instantaneous Hamiltonian, but what we do is a quench. So we let the system evolve normally, let's say as a standard quantum annealing Hamiltonian, up to a time tau q, after which we drastically change the annealing schedules of the protocol, and we set them constantly equal to some values that we are referring to as AQ and BQ, up to a time that is equal to tau q plus delta t. Delta t is the quench duration. And after this quench has occurred, we go back and set the values of the annealing schedules to the value that they had before the quench occurred. And we let the system evolve up to a time that is now greater than capital T and is equal to capital T plus delta T, so equal to a value that we will call T prime. In terms of energy landscape, what we see in this case is that the instantaneous eigenvalues of the Hamiltonian vary smoothly in time up to a time tau q, where the quench starts, and they are set to a constant value up to a time tau q plus delta t. After this time, the values continue varying smoothly. And due to this quench, the time-evolved state will go over some coherent oscillations that allow us to eventually retrieve the final ground state of HZ that we want to find in order to solve our problem. We will refer to these two proposals, and we want to use them to solve the maximum weighted independent set problem. In order to understand what is a maximum weighted independent set problem, we have to consider, first of all, a graph. So let us consider a set of nodes connected by edges. We give some weights to these nodes. In this case, for simplicity, we are assuming two families of nodes, which are omega naught and omega 1. And finding the solution of the maximum weighted independent set problems means, given a global weight W1 and W0 that can be attributed to some subgraphs, we want to find a partition of the graph into two subgraphs or more subgraphs that allow us to find the set that has the global maximum weight and that is also independent in the sense that its nodes do not have to be linked by edges. If we want to map this problem into an optimization problem, we can define a binary variable that assumes a value equal to 0 or 1 according to whether the node it is referred to belongs to the maximum weighted independent set or not. And what we have to define is a cost function that has to be minimized. And this cost function has to take into account the fact that each node has its own weight, but also the fact that we want to penalize the connection between two neighboring nodes. So the final cost function that we want to minimize is the H1 Hamiltonian with a constraint, which is represented by the Hamiltonian H2. Lambda is a Lagrangian multiplier that can be set according to how much do we want to penalize the connection between the neighboring nodes. If we map this problem into a classical spin problem, we will end up with a classical longitudinal field using Hamiltonian that now depends on some parameters that are Ci, which is the connectivity of each node within the graph, omega I, which is the weight of each node within the graph, and now lambda becomes a coupling constant between two neighboring spins, classical spins. And eventually, if we map this problem into a quantum problem, we will end up with our problem Hamiltonian that is exactly a longitudinal field using Hamiltonian. Hi is the local field that each spin will fill, and JZZ is now the coupling constant that rules the coupling between neighboring spins. The ground state of this Hamiltonian is is represented by the product state of up and down spins. And now the up spins represent the nodes that belong to the maximum weighted independent set. If we look at the bare instantaneous Hamiltonian, so without corrections, without non-stochastic terms, what we see, and we can see this from some results that have been shown in this paper that I've already mentioned, we see that there is a problem, that is the problem that I have talked about before, which is the closing of the gap, the occurrence of a gap that closes exponentially with the system size, almost at the end of the annealing protocol. So this is a problem. Solving the maximum weighted independent set problem means solving the problem of these gaps that close exponentially with the system size. If we look at the fidelity, so if we define a quantity which is the squared overlap between the instantaneous state and the time-evolved state, we can see that the final fidelity for this problem decreases in time, where the time now is the final time of the annealing protocol, and it reaches a minimum value that is always as small as we go to higher sizes of the system. And only after this minimum value, this final fidelity continues increasing. But of course, the range of values that we have to take into account involves values of final annealing time that are too high to be physically implemented. So this is of course a problem, and what we can also do is consider what happens at the instantaneous fidelity. So if we can focus on what happens for a 5-spin system and for a final annealing time of 2000, which is now T bar, what we see is that the time-evolved state instantaneously overlaps well with the instantaneous grad state, up to a time where the gap closes exponentially, where the Landau's inner transition occurs. And what we see is that if we compute the instantaneous fidelity between the time-evolved state and the instantaneous first excited state, we see that this fidelity raises to the value of 1 when this gap closes. So we can see that there is a perfect Landau's inner transition in this case. So that's why a good idea might be to introduce a catalyst Hamiltonian, so a non-stochastic term in the instantaneous annealing Hamiltonian. And in this case, we choose, following the references that I've mentioned before, an annealing schedule C of t that is the product of the two that we have already had and defined, so that this Hamiltonian will be 0 both at the beginning and at the end of the annealing process. And the catalyst Hamiltonian will be simply a coupling term between any two of the spins within the subgraph G1. So now we will have a further subgraph which we name GC, together with G0 and G1. In order to have a suitable correction in this annealing protocol, in order to exploit the diabatic transitions, we have to finely tune the value of JXX. Furthermore, if you're curious about how to implement this thing physically, there is a very recent paper by Banks et al. That show how to do it. So what we can see is that the gap is extremely sensitive to the value of JXX that we choose. That's why we have to carry out a fine-tuning of this parameter that is also dependent on the value of the size of the system that we consider. But the good news is that once we do the optimization for a fixed system size, we can keep this optimal value for any choice of final annealing time. In the other case, for the sweep-quench-sweep protocol, we also have to carry out an optimization procedure. Now we have to look at when the quench starts, how long it lasts, and what is the value of the Hamiltonian during the quench. Since A is actually always set equal to 1 minus B, we only have to look at B. So in this case, we implemented a grid search algorithm in order to find the optimal values of tau q, bq, and delta t, and we did it for different values of final annealing time, and we found the optimal value of fidelity that we wanted to achieve. In this case, we see that the value of tau q that is optimal tells us that the quench has to occur right before the gap closes, while bq is always set almost equal to 0, which reminds us of the process of reverse annealing, because we are actually doing a quench at a certain point, but we are restoring a value of the Hamiltonian that is similar to the initial values of the Hamiltonian. So in a sense, we are going back in time. And again, what I want to stress is that in this case, the optimization procedure is extremely sensitive to the value of the final annealing time that we take into consideration. So in this case, we have to carry out a different optimization process for each final annealing time. And this is bad news for this protocol. So to sum up what we are comparing two protocols that exploit diabatic transitions. In the non-stochastic diabatic annealing protocol, we alter the instantaneous energy landscape of the process, so to have a double closing of the gap instead of one. In the other case, what we do is altering the annealing schedule of the protocol. So instead of having a linear growth of B of t, we have a linear growth up to a time tau q, after which we set the value constantly equal to a value that is very close to 0. And after this quench duration, we set back the value of B of t to the value it had before the quench. In order to have a fair comparison between the two protocols, we have to stress that given that in the SQS protocol we have to evolve the sister for a longer annealing time, which is T prime, we will do the same also for the non-stochastic diabatic annealing protocol. That's why here you can see on the x-axis T prime on both the protocols. In this case, what I'm showing is the instantaneous fidelity in order to let you understand what's happening when the quench occurs or when the double closing of the gap occurs. In this case, for the non-stochastic diabatic annealing protocol, we see that the instantaneous fidelity that marks the overlap between the time-evolved state and the instantaneous ground state is constantly equal to 1 up to the time when the first gap closes. And this value is restored to a higher value only when the second gap is encountered. In the other case, what we see is the same thing up to a time when the quench starts. After the starting of the quench, the fidelity instantaneously starts oscillating, and it is eventually restored to reset to a value that is greater than 0. What is important to consider here is that in this plot, I'm not showing the actual quench duration that we choose for the numerical simulations that I'm showing, that I will be showing later. Because as you can see, we can understand how it's important to finely tune the parameters of the duration of the quench, since we see that during these oscillations, the fidelity goes back to suboptimal values. And if we are able to set the quench duration properly, we are able to find the proper optimal value of the fidelity after the quench, so as to completely and perfectly exploit the diabatic transitions. So in the unitary case, what we have done is comparing the results of the two protocols by looking at the infidelity. What we see is that if we look at the final annealing times that go up to a value of 1,000, we can see that at these short times that are proper diabatic, the SQS protocol outperforms the non-stochastic diabatic annealing protocol, and we can see it by comparing point by point the curves. And you can see that in this case, the orders of magnitude of the points are always smaller than the points in the orders of magnitude of this case. But what is interesting also to consider is that in the non-stochastic diabatic annealing protocol, we have curves that continue decreasing, curves of infidelity that continue decreasing as we go to longer final annealing time. And this is because at long times, adiabatic theorem holds for this protocol. And the fact that adiabatic theorem holds allow us to prevent Landau's inner transitions to occur both in the first and in the second gap that we have in this protocol. In the other case, on the contrary, what we see is that, especially for low system sizes, small system sizes, we see an effect of saturation. And this is due to the fact that we still have the adiabatic theorem that holds, but at the same time, there is also the quench that we have to take into account. And in this case, these results, these plateaus, lead us to think that going to higher annealing times is not as advantageous like it is in the NSDQA protocol. So now we are interested in adding dissipation. We are interested in doing this because, as I said before, in both the protocols that exploit diabatic transitions, we have to finely tune some parameters. So our suspect was that when dealing with some realistic implementations of these protocols, maybe the fine-tuning of these parameters could be damaged by dissipation, so by interaction with the environment. So in this sense, what we've done is considering now our quantum annealer as an open system described by a density matrix that evolves in time, and its time evolution is ruled by the Lindblad equation. So what we're doing is assuming a Markovian bath, and this Markovian bath is represented by the presence of these Lindblad operators that in our case were chosen to be always local. So they act like a sort of measurement on each node and on each side of our system. We have studied two types of dissipation that were both local. The first one is a local dephasing. The second one is a local gain and loss bath, and with some decay rates whose ratio remind us of the ratio that is typical of the detail balance ratio, so typical of thermal dissipation, even if in our case we are considering extremely simplified model since we are not taking into account the energy levels of the system. So in both cases we are carrying out some extremely simplified simulations concerning open systems, but we're fine with that because what we suspect is that given that the typical energy scales of our problem are set by the minimum gap that we encounter during the annealing procedure that are of the order of 10 to the power of -4 gigahertz, and given that the energy equivalent of the temperature at which these annealers work is of the order of about 1 gigahertz, we suspect, but we have of course to confirm this, that any kind of bath will act at the same way, in the same way, regardless of the details of the Lindblad operators that we choose. In this case, in order to compute the numerical simulations, we had to exploit the permutational invariance that is characteristic of the system. In this case, what we have to consider is that if we simply permute two spins within one of the two subgraphs by a permutation operator Pij, we see that the physics of the problem and of the optimization problem does not change. While if we do the same by exchanging two spins that belong to two different subgraphs, of course, the physics of the optimization problem changes. So if we define two permutationally invariant states for the two subgraphs, and we define the global state of the system as the product state of the two, which is still permutationally invariant, we can consider that since our Hamiltonian commutes with this permutation operator with arbitrary indices I and j, if we set the initial value of the state as permutationally invariant, it will be permutationally invariant for the whole evolution. And so for each subgraph, we can write this time-evolved state in terms of decay states, which are the eigenstates of the global spin operator for each subgraph. The quantum numbers of these operators S squared and Sc are j and m, and in particular the number of m values that we can encounter is 2j plus 1 for each fixed value of j. What is interesting and useful is that when we are in a permutationally invariant case, we can actually reduce ourselves in studying only the subspace with j equal to j maximum. So in this case, the number of states that we have to consider in order to have our simulations drastically decreases, and the system will scale eventually as n to the power of 2 instead rather than 2 to the power of n. But when dealing with dissipation, we cannot do this anymore because in principle, the Lindbladian can induce transitions into subspaces with j different to j max. So in principle, we could not reduce ourselves into the symmetric decay state subspace, but still we can consider that our Lindblad operators were local. And eventually, by looking at this, referring to this paper that has been published by Shamait Ali of 2018, we were able to exploit some and make some considerations that allowed us to reduce the Hilbert space we were working with, so that eventually the system would scale as n to the power of 6. Okay, so now I'm able to present the results in the dissipative case. First of all, let's consider the dephasing. What I have to stress is the fact that given that we wanted to see the effects of dissipation within the time window that we were considering, we set a value of decay rate which was the same for every final annealing time of the evolution, but that varied according to the system size. This choice was motivated by the fact that we know that the time at which the effects of dissipation come out are of the order of 1 over gamma times n if we have a local dephasing that is homogeneous all over the chain. So we chose a reference time that is equal to 1,400, which is at the midpoint of this time window, and we saw what happened. Looking at this protocol, these plots, I'm putting here the plots in the unitary case to have a fair comparison. And what we see is that at short times, the SQS protocol still outperforms the non-stochastic diabatic annealing protocol. And we again can see this by looking at the points and looking at the orders of magnitude of these points. And this is due to the fact that due to the choice of this decay rate, the dissipation is still starting to act. But after a certain T prime, that as we can see increases with the system size, the effects of dissipation come out, and after this T prime, the two protocols become equivalent. So it is interesting to consider that this value of T prime, this value of minimum of the curves, can be seen as a point of best compromise between dissipation and unitary dynamics. In the case of gain and loss dissipation, what we see is that, of course, the result is extremely dependent on the choice of beta, which was related to the inverse of an effective temperature of the bath we were considering. So for low temperatures, which is consists in higher values of beta, so the dotted curves here, we see that the results are qualitatively similar to those of dephasing, qualitatively, of course. And this is what we expected because we know that at these temperature scales, each dissipation affects the efficiency of the protocols, regardless of the details of the bath, which I was mentioning before. And for higher temperature, of course, the benefit of diabatic annealing is no longer seen, but is, of course, an extreme situation that may be far from a realistic case. So in conclusion, we explored and compared the effectiveness of two diabatic quantum annealing protocols, the non-stochastic diabatic quantum annealing and the SQS sweep quench sweep. We focused on the maximum weighted independent set problem, and we found that the SQS consistently outperforms the non-stochastic diabatic quantum annealing in terms of fidelity for shorter annealing times. The NSDQA demonstrated superior performance for longer duration due to its ability to effectively integrate adiabatic and diabatic dynamics. We introduced two types of non-unitary dynamics, dephasing and gain and loss bath. In the case of dephasing, up to a critical time, which increases with system size, the performance of the protocols remained comparable to unitary case. A suitable compromise can be achieved between the bath strength and the annealing duration without requiring experimentally infeasible times. And beyond the critical time, the infidelity grows exponentially with T prime, rendering the optimization and annealing ineffective. In future, it might be interesting to consider different decoherence models and other optimization problems. If you're interested about more details, you can take a look at our paper, which is now a preprint. And thank you for the attention.
Great, thank you very much, Giulia. Lots of interesting things there. A nice view of Naples, I guess.
Yeah.
Was that Vesuvio in the background?
Yes.
Yeah, very nice. Good, and yeah, I'll open it up for questions. So if anybody has questions, either unmute yourself or turn your camera on, or put them in the chat, or raise your hand, or all of the above. Maybe I'll start with the first question. You did mention this, but it went past pretty quickly. So you said that the sweep quench sweep protocol had more free parameters that you needed to optimize than the non-stochastic DQA. and that you needed to reparameterize for every anneal time. So can you just remind me how many free parameters are there in both cases?
In both cases, in the sweep-quench-sweep protocol, we looked at 3 parameters, which are the beginning of the quench, tau q, its duration, and the value that the Hamiltonian has during the quench. And this is the grid search algorithm that we implemented. I went a bit quick over this slide, but what we did is setting final annealing time and varying the parameters of tau q, bq, and delta t that I'm showing here in this extra heat map. So in this case, what I'm showing here is the heat map of the values of the fidelity while varying tau q and bq. But I still have to consider that in addition of the variation of tau q and bq, there was also the optimization over delta t that has to be considered. And so in this heat map, I'm showing the values of delta t that correspond to the values of the fidelity that I'm showing here. And this is what we have done in this sweep-quench-sweep protocol, which was new because the sweep-quench-sweep protocol was proposed, but not for the solution of the maximum weighted independent set problem. While in the other case, it was already known in literature by these 2 papers that only the optimization of this parameter had to be carried out. And this is due to the fact that, as I said before, the gap closes at an exact, precise point. So in order to induce a further diabatic transition, this choice of JXX had to be carried out with a high precision.
Okay, but on the sweep you said that the optimal torque Q was at the end of the anneal, I guess.
Yes, because the real the lightest shadow is encountered in this region of the heat map.
Yeah.
It's
so if one could possibly completely eliminate the optimization with respect to torque Q and just put it right at the end, would that work reasonably well?
It wasn't properly at the end of the annealing protocol. So I think that it was still important to verify it and see that what was the proper value. Now I don't remember the precise value, but it wasn't trivial. So
okay, it's a parameter you need to optimize. Right.
yes.
Good, thank you. Anapalafios has a raised hand.
Yes, hi. Thank you for the nice talk. So I actually had a question also regarding this same topic. I take it you also run this optimization for the dissipative case. Did you find? Yep. Okay, there you go.
Yes, you're asking me if we did this optimization procedure again for the dissipative case.
Yes, and whether you found differences in the landscape or whether it was harder to find the optimal region or shrinking.
Yes, actually, we performed this optimization procedure again for the dissipative case, but just to be sure that the shape of these heat maps could be seen as similar. So eventually, what we did is to consider the same optimal parameters for the dissipative case, which also makes sense because what we eventually want to do is to probe the robustness of these diabatic protocols under the effects of dissipation. So we want to see if the same parameters are suitable also for these protocols when we take into account dissipation. So we verified it, but we also wanted to use the same parameters. So
all right, thanks.
Any additional questions? Did you look at the time dependence of your state overlap metric in the open system case?
can you repeat the question? Did we look?
did you look at the time dependence of during an anneal? You plotted earlier on the overlap between the instantaneous ground state and the final ground state, and did you do that in the case where
Yes.
dynamics?
Yes, we did it. I didn't plot them here. What we see is that due to the effect of dissipation, there is something that occurs in between. For example, in the case of the, I'm trying to find the unitary case. Maybe it's before, but maybe I will simply talk about it by words. We see that there is something that occurs, for example, in the non-stochastic diabatic quantum annealing protocol in between the two closings of the gap. So eventually, the final optimal fidelity that can be found, of course, is lower in value due to the effect of dissipation that has altered the behavior of the instantaneous fidelity between the two closing of the gap. And this would occur also in the sweep quench sweep protocol.
Do I understand? Do I understand correctly if I say that the following metric is the important one? It's a comparison between your dephasing time, the time interval between the two minima in the DQA case. Have I understood that correctly?
You mean this thing? I will. Here, you mean this? I don't know if I've understood the question.
Yeah, so I guess you mentioned that dephasing between the two minima is an important event that will mean you end up in the wrong ground state. So presumably maybe the x-axis I would be more interested in seeing on these plots is the time between the two minima rather than
yes, I see.
total anneal time.
Here.
Yes.
In this case, the two minimum in energy.
Exactly. That time difference seems to be the crucial time scale to compare your dephasing time with. Am I understanding that correctly?
Actually, this is not something that I've thought about before, but it might be interesting to consider. Yeah.
Okay, good. Any other questions from anybody in the audience for Giulia? If not, let's thank Giulia once again, or in fact, possibly the first time. I forgot the first time, sorry. A round of applause from me on behalf of the audience members. And thank you very much for a very interesting presentation. And I look forward to seeing as many people as possible at next week's seminar, which is going to be about protein folding simulation using quantum annealing given by Anders Ehrbeck. So I'll see you all then. Thank you, Giulia. Bye-bye, everyone. Bye-bye.
Thank you. Bye.